Section 3.7, Linear Programming. So we're going to do a linear programming problem, which is a system of linear inequalities like we did last time, but an application of those. So it says this furniture company makes end tables and coffee tables out of premium cherry wood. Each table must be manufactured and stained. Each end table takes 4 hours to manufacture and another 4 hours to stain. Each coffee table takes 8 hours to manufacture and another 12 hours to stain. The company also knows from previous experience that it can make no more than 15 end tables per business day. So the company can employ at most 160 manufacturing employee work hours and 180 stainer employee work hours per business day. So these restraints would be because of funding and money available. Each end table brings a profit of $40 and each coffee table brings a profit of $65. Of course, we want to maximize our profits, so how many end tables and how many coffee tables should this company make per business day? So the first thing we want to do is just label what our unknowns are. What are we looking for? So labels. We're going to let X equal the number of end tables per day, and we're going to let Y equal the number of coffee tables per day. Alright, so that means that if we make X number of end tables and we make $40 for each of those, that 40X equals the profit on end tables. Similarly, 65Y equals the profit on coffee tables. And of course, we're going to say P is the profit, total profit. That's what we want to maximize, of course. All right, so here's everything nice and labeled. Now we want to write out our objective function. Right, and that's whatever we want to maximize in this case, or we could be minimizing something as well in a different problem. So our total profit, of course, is however much we make on end tables plus however much we make on coffee tables. So there's our objective function. So now that we have our objective function, we're going to write out our constraints. So the problem gives you all of the constraints. However, some are actually implied. For example, in this problem, we know that we're not going to make a negative number of any kind of table. So the number of tables each have to be greater than or equal to 0. They could be equal to 0, right? We could make none of that particular type of table. So these two are implied. So now let's talk about the ones that we get from the problem. Alright, so we do know that we can make no more than 15 end tables per business day. So that means X is less than or equal to 15. And then we're going to have one inequality for the manufacturing hours and another one for the staining hours. Alright, so we get 4X plus 8Y. So these are the manufacturing hours for the end tables and the coffee tables. That has to be no more than, which is less than or equal to, 160. So that's the manufacturing hours. We do the same thing with the staining hours. We get 4X plus 12Y less than or equal to 180. Those are the staining hours. So now we have all of our constraints. Because we're dealing in only positive values, we know that we can graph strictly in quadrant 1. That makes our job just a little bit easier. So I'm going to start graphing in a moment in quadrant 1, and we need to put these 3 lines on the graph, and then we're going to talk about the feasible region. So again, because we have x and y both greater than or equal to 0, we are in quadrant 1. All right, let's do the easy one first. X less than or equal to 15. So we go 5, 10, 15, and then we're going to draw a vertical line here. All right, and that's the line x equals 15. But of course the inequality is less than, which means we're going to the left, but I'm not going to shade until I get to the end. All right, so now let's do the other 2. So the first one I'm going to do is 4x plus 8y equals 160. So I need to graph equal, right? I need to graph the boundary line. All right, so to do that, I need a couple of ordered pairs. You could put this in slope-intercept form, but I'm just going to use the intercepts because the coefficients both divide this number over here. So I need 2 ordered pairs. And again, I'm going to use the intercepts. When I put 0 in for x, I get 4 times 0 plus 8y equals 160. That gives me 8y equals 160, so I get y equals 20. And then if I put 0 in for y, 4x plus 8 times 0 equals 160. That's 4x equals 160. So we get x equals 40. So I'm going to go ahead and graph this line. So I need 0, 20. That's right here. And then I need 40, 0. That's right here. And I'm going to graph my line. And even though it is color-coded, that's in blue, I'm still going to label this. This is 4x, sorry. Oops, all right, cut that for just a second, and then we'll go back to this as soon as I write this out. All right, so pick up here. This line, this blue line, is 4x plus 8y equals 160. And now for the second one. Second line I'll do in red, 4x plus 12y equals 180. And again, I'm going to graph this using the intercepts. So when I put 0 in for x, I get 4 times 0 plus 12y equals 180. That's 12y equals 180. So I get y equals 15. And a second ordered pair, I'm going to put 0 in for y, so 4x plus 12 times 0 equals 180. It gives us 4x equals 180, so x equals 45. All right. So I have 0, 15, it's right here. I need to go to 45, so it's going to be out here. That's 45, 0. And now I'm going to draw this line. And I'm going to label this line 4x plus 12y equals 180. So now we want to find the feasible region. The feasible region is the region where if we shaded all of these solutions, we would have an intersection. All right, so what do? We look and see what's going to happen. It would be easy to look up here in this enclosed area, but if you do a test point here, you will see that it doesn't work for some of the lines. So you can do some test points if you like. I'm going to show you where we're going to shade. This is our feasible region. All right. Again, you can do some test points if you like. And what does that mean? That means that now I know where my vertices are. I have this one, this one, this one, and this one. Well, what is this one? Well, you can trust your graph, and you can even trust me if you want to. All right, this point is 1510. If your graph was not very good or you weren't sure, this is where two lines intersect. So of course you could set up a system of equations and solve that system for the point of intersection. So that is another option for you. So now we have 1, 2, 3, 4 vertices. So I'm going to go to the next page, and what we're going to do is we're going to identify our vertices, and then we're going to evaluate the objective function at each of these vertices. All right, so we used our graph to find all of our vertices. Here they are: 0, 0, 15, 0, 15, 10, and 0, 15. So we need to evaluate the objective function at each vertex. All right, so at 0, 0, we get p equals 40x plus 65y. So that's 40 times 0 plus 65 times 0, which of course is 0. We've evaluated this one. Next we need to evaluate at 15, 0. So we get p equals 40x plus 65y. It's going to be 40 times 15 plus 65 times 0. That gives us 600. We've evaluated the second one. At 15, 10, again we have p equals 40x plus 65y. That's 40 times 15 plus 65 times 10. That gives us 1250. We've evaluated the third one. And last is at 0, 15. We get p equals 40x plus 65y. That is 40 times 0 plus 65 times 15 gives us 975. Now we are looking for the max, which is this number right here. And that's good, that's the maximum profit, but we need to talk about what that means. So here's our final answer. Our max profit is $1,250 and happens when the company makes 15 end tables and 10 coffee tables per day.